Hey guys, we're going to be starting next section. We're starting on textbook page 244 using corresponding parts of congruent triangles. So the main idea for this is we're going to be first given a problem, you have to prove triangles are congruent using one of the four ways, and then SSS, SAS, ASA, and AAS. And then from there, we say that because these triangles are congruent, then their other corresponding parts are also congruent. So it's one more step in the proof. So prove the triangle is congruent, and then you do one more saying that since these triangles are congruent, these two corresponding parts would also be congruent. So we have a problem here. I'm going to go through it. So we are given two triangles like this. We are given that KBC, this angle here, and angle ACB, this angle here, is congruent, and then BKC, so BKC and CAB over here, those are congruent, and we need to prove that this line is congruent to this line. So this proof, we have two angles, so we're going to have to use either ASA and AAS. We're not going to be using ASA because if we need ASA, we would have to show that these are congruent. That's what we want to need at the end. What we have here is we have CB. So we have CB that is congruent to CB. And the reason for that would be reflexive property. So we can go through this proof by showing the one. We have the angle KBC is congruent to angle ACB, and for that would be given. Then the second part would be angle BKC congruent to angle CAB, and again that's given. And the last part for proving these two triangles congruent would be CB is congruent to CB, and that would be reflexive property. So we have this reflexive properties. This part over should be over here. Apologize for that. Then we can prove that these two triangles are congruent. So we could say triangle KBC is congruent to triangle CAB. And the reason for that congruence would be AAS. Remember that this side is opposite of this congruent side, which is the same as this congruent side. So the side is opposite of the same congruent side. So we need one more step. We need to prove that these things are congruent, these lines are congruent. So we could say that they are congruent. KB and AC are congruent. This side is this side are congruent. The reason for that is you would say this whole thing, I'm going to put it down here. Whenever you are doing for corresponding parts, you're going to say corresponding parts of congruent triangles are congruent. Now for a proof, you can say, you can write this whole out, or you can just say corresponding parts of congruent triangles are congruent. You can write exactly how it's written here. So this would be this reason over here. I can't move it anymore, but you get the idea. Alright, moving on to angle E. So we want to show this one is congruent to this one here. Okay, so let's go through the proof. First one we're going to start off with is BA is congruent to AE given. 2, CA is congruent to AD. Again, it is given. Next one, we have two sides, and we need something else. We are going to we can't show this side and this side are congruent, so we're going to have to do something else. So we have to use an angle. Well, we're not going to use this one because this is going to be after our proof. We're not going to do this one because we don't know. We can use this angle, angle CAB, and angle DAE. And the reason for that is because they are vertical. So we could say angle CAB congruent to angle DAE. Vertical angles are congruent. After this, we can say that these two triangles are congruent. So triangle CAB is congruent to triangle DAE. And the reason for that would be SAS. After that, we can show that these poorly drawn angles would be congruent. So angle C is congruent to angle E, and the reason for that is corresponding parts of congruent triangles are congruent. And you could even use the symbol for congruent here if you want to be extra lazy for that. Especially you, Angus. I know you will. Okay. So let's go through a word problem with this. Okay, so this word problem says, Thales, a Greek philosopher, said to have developed a method to measure the distance to a ship. He made a compass, so the thing you use to draw shapes, draw lines and perpendicular lines, the thing we use, by nailing two sticks together. Standing on top of a tower, he would hold one stick vertical, up and down, and tilt the other till he could see the ship. So he would have one stick on the ground on the top of the tower, and you'd have the other end where you had like the pencil part of the compass sticking out until he could see the ship. With the compass setting, he would find a landmark on the shore along the line of the tilted stick. So he would turn it around and find a landmark that is at the same place of the compass setting. How far would the ship be from the base of the tower? So we are given a couple of things. We are given this this triangle here, and we can imagine that this is the tower of the triangle. And we have different points. S is the ship, L is the landmark, R is this bottom point, and T is the top of the tower. So we're given a couple of different things. This should be RT, RTS, not RTA. Alright, so angle RTS is congruent to RTL. So these two angles are congruent. Then this angle here is a right angle, and this angle here is also a right angle. So we need to show that these two triangles first are congruent, and then that this here, so I'm going to put this in orange, we want to show that this is congruent to this. Right, so going through, our first one is that angle RTS is congruent to angle RTL. given. 2, we could just say that angle RT, sorry, not TR RTS is congruent to angle STL. And that is because right angles are congruent. After this, we have two angles. So we're going to have to use one of the two double angles theorem. We don't know about TL or TS, or we could do TR and TR. Well, we know TR and TR are congruent because they're the same. So we could say that TR is congruent to TR, and that's because of reflexive property. So then now we could say that these two triangles are congruent. So triangle STR is congruent to triangle RTL. And that's from ASA. And then finally RS is congruent to RL, and that's because of corresponding parts of congruent triangles are congruent. Oh, almost fits. Almost fit. Darn. I made one little mistake here. This should be RTS here. So right here should be RTS. Alright, we're going to do 2 sections today, so we're also going to be doing the next one based on isosceles triangles. Okay, so this would be an isosceles triangle. In the isosceles triangle, you're going to have two sides being congruent. These sides that are congruent are going to be called legs. So the legs are the two congruent sides. Then you're going to have a special angle. A special angle here is called the vertex angle. So the angle up here is called the vertex angle. Okay, so the vertex angle. Then at the bottom here, we're going to have two other angles here. So down here, we have the base angles down here. An important part about isosceles triangles and these base angles is that base angles and isosceles triangles are always going to be congruent. And that's a very, very important aspect to these things. It's actually the first theorem we have. So if we have two sides in a triangle being congruent, then the angles where these two sides do not meet are congruent. So if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So opposite that side is congruent, opposite that side is also congruent. So that is the main proof for that. This also works in the converse of this. So for the converse of this proof also works. So if two angles of a triangle are congruent, then the sides opposite the angles are congruent. So it's also a very important part about this proof. And we can use this proof and these different theorems to prove a lot of different things. So here I'll give you an example for you. Okay, so here's an example. We have two triangles, one much bigger, one much smaller. So we have triangle ABC, the big one, and triangle ADE, the smaller one. And we are asked these two different things, and we're going to be asked yes or no, basically. So first one, is AB congruent to CB? Is this whole AB congruent to this CB? What do you think? So this would be yes. They are congruent, but why are these two congruent? These two would be congruent because we have this angle here and this angle here. These are congruent. So when we have angles, two angles are congruent, then these sides are also congruent. So we could say yes, because angle A is congruent to angle C, so the converse of the isosceles triangle theorem. So the theorem we had before was called the isosceles triangle theorem, and this would just be the converse of that. And then down here, is angle A going to be congruent to angle DEA? Is this angle here also the same as this angle here? Well, we have in this triangle sides being congruent. So since the sides are congruent, the opposite angles are congruent. So again, we have yes, because the sides are congruent, so the opposite angles must be congruent. Alright, we're going to move on to the next theorem. Okay, so the next theorem is if we are given another isosceles triangle like this, and we're told that we have a perpendicular bisector here. So we have this triangle, this angle, and this angle are congruent. These angles up here, ACD and BCD, are also congruent. We have a perpendicular bisector here. So if we have these things, we're going to have something else, which is if AC and BC are congruent, and ACD and AC and BCD are congruent, then this line here is perpendicular to here. So we're going to make right angles here. Beautiful right angle. And AD and BD would also be congruent. So that theorem here says if a line bisects the vertex angle of an isosceles triangle, then the line is also perpendicular to the base. So if we have a isosceles triangle and we have an angle go through the vertex angle, remember that is the top one, then it's perpendicular to the base, and it also makes the base length, this base segment, into two congruent parts. So it's a perpendicular bisector here. So I'm going to go through a question. Okay, so for our example here, we have a triangle split into two, and we're told that AB and BC are congruent, and we're asked to find what is the value of x when the measure of angle A is 54. So to do this, since AB and BC or CB are congruent by the Isosceles Triangle theorem, angle A here is congruent to angle C here. So that means that angle A is going to be 54 degrees, so angle C is now 54 degrees. Then we are told that this line comes down and breaks this 2 into 2 congruent parts. Based on the theorem from just before, if a line comes down from its vertex angle, that means it'll come down as a perpendicular bisector. So this line here will be a perpendicular bisector. That means this angle will be 90 degrees and this angle will be 90 degrees. So since BD bisects angle ABC at the top, is it BD? That should not say is it, should be it is BD perpendicular to AC, which makes the measure of angle BDC 90 degrees. So BDC is 90 degrees. So now we have this is 54, this is 90, and this is x. So that small triangle can be 54 plus 90 plus x equals 180, and then x would be simply 36 degrees. Alright, we only have one more thing we need to get done for this lesson. And to start off with is something called a corollary. A corollary is a theorem that can be proved using another theorem. And we have the corollary to the first two theorems that we had earlier. So first one is if we have 3 side lengths of a triangle being equal, that means the angles will be equal. So if we are given a, I don't know why this is colored like this, that's why. Okay, so if we have a triangle like this, more similar to this actually, and we are told that these 3 sides are congruent, side Z, X, and Y, then the angles would be congruent. So if ZY is congruent to XY is congruent to ZX, then angle Z is congruent to angle Y is congruent to angle X. So what that is basically saying is if a triangle is equilateral, then the triangle is equiangular. Now this can be shown in the opposite way as well. So this could also be shown is if we are given this first, then this could happen. So converse is also true. If a triangle is equiangular, then the triangle is equilateral. I'm not going to show a picture of that again. It's just basically the converse, so you could just flip it. Alright, so that is it for this one. I know this is a little bit longer, but we had to do 2 lessons for today. So in class we're going to do starting off with some homework, and then we're going to do into an activity.